In transistor circuits, the DC sources set up DC currents and voltages. The AC signal source produces variations in currents and voltages. The circuit analysis should get split into two parts. To avoid confusing AC and DC currents and voltages, we will use capital letters for DC quantities. For the AC currents and voltages, we will use lowercase letters. The signal frequency we are immediately concerned would cover a range 20 Hz to 20 kHz. The design route we follow may not be exactly 100% accurate, but would ensure accuracy to the tune of 90%. Accuracy may be important near the end of an analysis, but during the early stages, it loses its value. Referring to the dynamic IE-BBE characteristics of a typical transistor, it may be noted small signal, the operating point swings from Q to A, back to Q, down to B, and back to Q. This cyclic of event gets repeated, being located in an essentially straight portion of characteristics. The changes in voltage and currents are directly proportional and can be shown as delta VBE is equal to K into delta IE. Where delta stands for the change in and K a constant of proportionality. Changing the peak value of any small signal does not change the value of K. This constant K is quite important to us, representing the value R dash E, where R dash E is equal to K, which is equal to delta VBE over delta IE. Because AC current and voltage are identical to the changes in total current, we can rewrite the expression R dash E is equal to VBE over IE. For instance, if VBE is equal to 25 millivolts and IE is equal to 1 milliampere, R dash would be 25 millivolt by 1 milliampere, which is equal to 25 ohms. By using calculus to find the slope, we can prove that R dash E is equal to 25 millivolt over IE. The AC beta is a small signal quantity and is defined as beta DC is equal to delta IC over delta IB. Beta AC is equal to IC over IB. The quantity H of G is the DC current gain generally shown in data sheets. Do not get confused as this HFE is the same as beta AC and is mostly equivalent to beta DC. This is our first approximation in our exercise. By taking as many effects as possible into account, we arrive at AC equivalent circuit of transistor as shown in figure. In this representation, all DC voltages are short circuited. All condensers are shorted. We often measure transistor voltages to ground with voltmeter. For this reason, one should know approximately what AC voltages exist in the circuit. The three basic AC voltages in any transistor amplifier are 1. Collector to ground voltage VC, 2. Emitter to ground voltage VE, and 3. Base to ground voltage VB. It may be shown that VC is equal to IC into RC, VB is equal to IE into R dash E plus RE, and VE is equal to IE into RE. In summary, we can reduce the AC equivalent circuit of an amplifier to the base driven prototype. We can now calculate the AC emitter current. Once we have this IE, the rest is quite easy.